up, I'm going to ask Nick Battaglia to start in on his presentation, and we will go right to Nick, and then we will have a break, and then we will head to the panel discussion, probably looking now more like 9:10. Yeah, and Grant.
Well, I can see we're pressed for time here, so I will skip ahead to first saying thank you to the organizers, and especially letting the SZ infiltrate this meeting. It's been great. You guys have been very accommodating, and I'd also like to thank all the participants. Many of you have had discussions with. It's been really enlightening, and it's been very educational for me. So I've really enjoyed these past 8 weeks when I could attend and I wasn't, say, lecturing as I was just an hour ago. So I will keep the intro as brief as possible. I hope it's not a surprise to anybody that I'm talking about the SZ, because if it is, I've done a bad job over the past 8 weeks of telling you what I'm interested in. But for those who don't know what the SZ effects are, I'm only going to be mentioning 2. There are more. I'm going to be talking about the inverse Compton scattering of CMB photons and the Doppler boosting of CMB photons as they interact with any free electrons along their path towards us. So the inverse Compton scattering is known as the thermal SZ, and this is proportional to the line of sight pressure over here. And this effect is roughly, a factor of 10 to 100 times weaker than our normal CMB fluctuations. The next effect is the kinematic SZ. This is the Doppler boosting of the CMB photons, and that's proportional to the line of sight momentum of these free electrons. And that is a slightly weaker effect. They have different scalings with the mass of your halo, but this is about an order of magnitude below the thermal SZ. And as we heard from Aurora, right, I think we can all agree that making maps or making a full map of the thermodynamic properties of the CGM is very, very exciting. And what I hope to convey to you is that we can do that with these various effects. I haven't told you yet how we're going to do that. And what's really nice is that this inverse Compton scattering or spectral distortion that we see from the thermal SZ and the Doppler boosting from the kinematic SZ, these are all redshift independent, right? You don't suffer from cosmological dimming. So in principle, you can measure these out as long as you have large enough samples out to whatever redshift you want, right? And I'm particularly excited about the KSZ because there's been an emergence of KSZ detections just over the past decade. So the first measurement of the KSZ was actually done almost a decade ago. This was work led by Nick Hand and the ACT collaboration shown in this upper right, and this was the first 4 sigma detection. And over time, over the past 10 years, various groups, collaborations have made SZ or kinetic SZ detections on various different samples using different estimators. And these are all, this isn't a complete list, these are just some examples of detections that were made all roughly around sort of 4 sigma. So just at what physicists would call the detection limit, right? The thermal SZ has been measured for several decades now, back into the 80s. But if you'd like to see recent measurements of, in particular, thermal SZ observations of the CGM, I would refer to you to talks by Joel Bregman and Evan Scanapieko earlier on in the workshop. They were really excellent. So I mentioned the kinetic SZ is a detection of the line of sight momentum, right? That's not density yet, right? So how do we get to density? Well, there was this neat method proposed by Shirley Ho and collaborators back over a decade ago, where you take a CMB map, right, and you cross-correlate it or stack it on a velocity reconstruction map. And what I mean by velocity reconstruction, this is something that's typically done for baryonic acoustic oscillations and spectroscopic samples. You basically look at the overdensity of your galaxies, and that relates to their peculiar velocities that they have. And it's a simple sort of in the linear regime reconstruction of where those galaxies actually came from. So if you have this weighting of a galaxy's velocity, you can correlate it with the CMB temperature map, and that should pull out the kinetic SZ effect, because nothing else, the primary CMB fluctuation shouldn't care about the velocity of that galaxy, nor should things like dust to first order, or say even the thermal SZ should not correlate with the velocity of that galaxy. So if you take a bunch of pictures of galaxies in the CMB map and weight them by their velocities, whether they're moving away from us or towards us, you can then pull out a map of the density. If you do this correlation, which I'm showing you up here, is proportional to the RMS velocity of the peculiar RMS velocity of all galaxies. So this is something we can actually calculate from cosmological theory. So given some cosmology, we can get this amplitude. And then what's left over is you can measure then the density profile as a function of radius. Okay, and this was actually first demonstrated on data by some of my collaborators, Emmanuel Chan, Simone Ferrara, and the ACT collaboration. So we have, using this particular technique, a measurement of the cumulative free electron density profile. And this is unbiased. So if you have free electrons there, this doesn't depend on temperature or anything like that. Any free electrons will be picked up by this kinetic SC effect here. Okay, so what's great is now we have, measuring the line of sight pressure is easy. We get that through the thermal SC. That's been done for years. And now we have the ability to measure density profiles. Okay, people have thought about previously combining thermal SC and kinetic SC. That was to get more, getting at the temperature or the peculiar velocity or the optical depth of a particular object. What's sort of new now is we're thinking about this in terms of actually extracting CGM properties. So getting at these thermodynamic properties, the pressure, the temperature, the density profiles. And we can do this out to large radii. Okay, so that's really nice. It's both a pro and a con. It's part of, we can't really do the inner radii because of the beam, but because of the beam, we can also do the outer radii. So it's a trade-off there. So I know we're supposed to talk about future measurements. These are, within the past 6 months, we put this on the archive. I think this is my way of motivating why I'm so excited about the future measurements to come, because of what we can already do or just did. So this is just showing our recent kinetic SZ profiles from ACT, where we took the BOSS CMAS sample and cross-correlated that with ACT using this velocity reconstruction measurement method or estimator. And as you can see here, we have a nice density profile. In the dotted lines, at different frequencies, in the dotted lines, you can see what it would look like if the gas followed dark matter. Now, I don't need to tell anybody here in this conference that the CGM and the profile of the CGM density looks nothing like the dark matter halo, but you'd be surprised what cosmologists do on small scales. So we thought we'd put this out there anyways. So as you can see here, this measurement here is now about depending on how you count, whether it's from the null or the actual detection of the profile, it's about an 8 sigma detection of the kinetic SC, so doubling our previous detections. We also, as I said, for free, get the pressure profile. So this is the thermal SZ, and that's shown here. Again, it's a decrement at the frequencies that we're looking at. So I just wanted to highlight with the TSE, you have to be particularly careful about dust emission in these galaxies. Galaxies do have dust in them, as we know. So you have to use foreground separation techniques. And I'll mention that a little bit at the end in future observations. And now here comes the full thermodynamic information. We have density, we have pressure, we can also get temperature, right? We have, our pressure is basically our optical depth times the temperature. Our density is our optical depth. You take the pressure, you divide it by the density, and you get a optical depth weighted temperature. That's shown here. So we've measured the temperature profile now in these CMAS galaxies. Just to point out, this would be the prediction of the virial temperature of these galaxies. They're about 2 or 3 times 10 to the 13 solar masses, and this is the profile that we measure. Okay. And this, I should mention, this is all work led by Emmanuel Chan, Simone Ferrara, Stefania Modio, and Emily Mosier, who made it off, was one of the 5th authors. Now, all this being said, these are not measurements of individual objects. Okay, so I hope you're okay with that. These are average quantities. These are for the entire sample. And so when you do that, or anything in general, right, it's a good idea to have some model for the stack. And so what we do all the forward modeling in this 3D profile. So we do this with simulations, or you can do this with your favorite parametric model. I'm looking at Mark. And what you can do then is forward model it through your instrument to get out into the observable space. And we have a whole pipeline to do this. So given your density profile, pressure profile, you stick it in here. modeling various terms and your sample. You run it through our pipeline, including beams, whether you have a Gaussian beam or the actual beam, and then you do your aperture photometry and you get out your 2D observed profile. Okay, and then once you have that, you can make inferences like how much energy compared to the binding energy was injected in these halos. Remember, the thermal energy or the integrated pressure along the line of sight has memory about all the feedback processes that went on in that halo, right? So we actually, when we measure this, we have information about some of the physical processes that happen inside that halo. We've heard a little bit about non-thermal pressure support. You know, given your parametric model, you can also, if you measure the density and pressure, you can extract out things like the amount of total non-thermal pressure in cosmic rays, magnetic fields, turbulence, large bulk flows, rotation, if that's in your parametric model. And so for this particular parametric model, we made some constraint that it had to be less than 20%. Another great thing you can do is these large radii of the CGM have been, until now, not probed very, very well, I will say. And so cosmological simulations like Illustris, like Eagles, like Simba have made predictions for what these profiles look like, right? They can't tune their numerical simulations to these observations because they didn't exist when they made the simulations. So these are genuine predictions. And what it looks like right now is you can ignore. One of the great things about forward modeling is you can also bring it back into, what I would call theory space, thinking about 3D radial profiles. That's what a lot of us like to think about, at least theorists do. And you can go back and you can make comparisons in that space as well. So focus on the bottom panels here because these are, the error bars here, at least at large radii, are correlated. And what you can see here is that the density predicted by these simulations, including some of my old simulations, actually do okay. They're at the bottom envelope of the density profile as predicted by the simulations, but they seem to be really lacking, I would say, pressure, or they're not hot enough in these outskirts, right? The pressure is much below. So this is this blue, dark blue curve here with the band is sort of the 2 sigma region allowed by the data for a parametric fit. So just a simple parametric model, and this is what's predicted by these simulations. So the pink and the green and the orange. Okay, so this is really neat. We're really excited about this. We're able to now test these large cosmological simulations, and so that's the results as they are today. And that's great, but my task is to talk about future observations. So I will say, the results I've just shown you are already promising, but this is just the beginning, right? We're just scratching the surface or the potential of what we can do with the thermal SC and the kinetic SC. So these sort of, 6 to 8 sigma observations we're making of profiles, in the not too distant future, we'll be making density profiles that are 5% or less. In 10 years from now, we estimate, or we forecasted that we can actually make percent level or sub-percent level measurements of the density profile, which is really cool. So this is showing you some of the forecasts I did a while ago. I knew I was going to give this talk 4 years ago when I wrote this paper, and this is just showing you what we can do with some upcoming, I would call them stage 3 experiments and stage 4 experiments, cross-correlating with various surveys. The survey we had back then, we did for the yellow is the CMAS survey. For the gray bands, this is the DESI survey, which is on the sky now. And these improvements are coming from many things, right? They're coming from potentially better resolution of our CMB experiments, coming from lower noise from our CMB experiments, and just having larger galaxy samples, right? So again, percent level measurements in about 10 to 15 years from CMB stage 4, cross-correlated with DESI or maybe something better, and definitely sub percent level measurements of the pressure profile using these techniques. So that's really cool. And so where are these coming from? I've mentioned this before. I didn't want to go into too much detail about the experiments, but for CMB observations, we're photon noise limited. So what that means is you want to get lower noise maps, you either integrate for longer or you throw more detectors on the sky. And that's what these future experiments are doing. So CCAT Prime, Simon's Observatory, SPT3G, Advanced ACT, we are putting more and more detectors on the sky every day to get lower noise CMB maps, right? CMB stage 4 is another step above that. The actual growth in the number of detectors on the sky actually follows like a Moore's law. So if we just keep waiting a little longer, the measurements are going to get better and better. We're packing more and more detectors into our cryostats. We're making larger and larger fields of view so we can pack more detectors in there, make larger survey telescopes. So we're getting more detectors, and another advancement is we're getting more frequencies on the sky. So more frequency bands. The more frequency bands we have, the better we can do things like component separation. Another advance, if we think a little further in the future, is higher resolution. So the measurements I showed you, right, we're resolving maybe 1 or 2 elements inside the virial radius at about redshift 0.5. If we go to lower redshifts, we can, we can actually expand that, get many more resolution elements inside the virial radius. But if you really want to get down to sort of the tens of kiloparsec level, you really need bigger dishes. So this is at last here, towering over the ALMA telescopes, right? This is potentially a 50-meter dish in the Atacama Desert. There's also CMB HD, which is another one, which is even further field. This is again, like a 25 to 50-meter dish, improving the resolution that we have by factors of 5 to 10. Okay, so these are 2 big improvements on the CMB side that we are looking forward to. And another one that we're looking forward to is just larger samples, right? So with the Vera Rubin Observatory coming online in the next couple of years, that will produce a large number of, like a huge galaxy sample that we can then cross-correlate with and beat down some of this noise, especially on large scales, because those error bars also, some of them reduce depending on where they are, what angular scale you're looking at, they reduce like 1 over square root n. DESI coming online will be great. If you want to do this velocity reconstruction method, you need a spectroscopic sample. So DESI is producing a huge spectroscopic sample compared to what we have already with BOSS. And just to be a little provocative, right? So looking ahead to CMBS4, this is work that Colin and Marcelo and the decadal survey review for CMBS4 worked on. I helped out here a bit, and we had some input from lots of simulators. This is just showing sort of the error bars we get for a CMAS or DESI-like sample at high redshift, so redshift 1, right? And this is showing you the various predictions from the current cosmological simulations. And I guess this is provocative, maybe it's not, CMBS4 will rule out all current models. I say current models of galaxy formation. But then I put down, we've already kind of started to do that already with ACT. Yeah, so is the emoji. This is showing you, we're going to have these huge signal to noise numbers. We can actually start doing fun things with that, right? Like there's no point in measuring sub % pressure profiles and density profiles. You can actually start subdividing them up, right? If you have this as a function of redshift, your favorite galaxy type or property, we can start looking at how the pressure and density and temperature profiles look like in these different samples. So that's, again, really exciting. This is an example for LRGs. This is an example for quasars. We can do this at redshift 2, right? We have enough quasars with DESI that we can actually reconstruct the CGM of a quasar at redshift 2 and its thermodynamic properties. I think that's really cool. I don't know. Maybe you do too. Here's another sort of signal to noise propaganda plot that Colin and I put out in our white paper that we wrote for the decadal. This is just showing signal to noise of a different estimator. This is the projected fields estimator. If you want to know what this is and the latest measurements, I encourage you to look for Colin's talk from a couple weeks ago. They've made some really nice measurements and strides forwards with this. You can see here, this was sort of where we made our first measurement. It was around 3 sigma. We were supposed to get to 100 sigma. We're still getting there. We're not quite there yet, but this is sort of the trajectory that we expect. Maybe you shift these dates a little bit because people get busy and we haven't actually gotten to doing these observations yet. I will point out that, again, this is a stack. All these observations are in a stack. Jess, I'm almost done. Once the signal to noise gets really high, when you get really high signal to noise, you just have to really worry about these little things, right? Things you didn't necessarily have to worry about so much when we were stacking at say 6 sigma or 8 sigma. And so Emily Mosier, who's a student who's working with me, not a postdoc yet, but eventually, she put out a paper. It's actually out on the archive today. We hope to put up a video very shortly on the site, or on Slack and on YouTube, for everybody to look at. And this is just showing you that the modeling choices that you make for modeling that stack really start to become important, even when you go to not even CMBS4 level, but even like Simon's Observatory, CCAT Prime, Advanced ACT. They really start to become important. You can potentially bias your inferences if you don't include things like a contribution from other galaxies around your galaxy, or you don't actually take into account that the distribution of galaxies actually matters for things that don't scale linearly with mass, right? An average mass won't cut it. You actually want to model the full distribution of your galaxies. And this is a slide just to say component separation, dust is important, but this is a well-studied problem in CMB, in the CMB community. There are solutions that are already implemented on data. We expect them to work on, higher fidelity data, but, and I'm optimistic they will. And an advantage that we're going to have is these future CMB surveys will have a much larger range in frequency coverage, which makes this job even easier. So I will leave you with this, right? I think we're all in agreement. My task was maybe to convince you that the SE will be important for understanding the CGM in the future. I think we all agree that thermodynamic profiles are important. So let me pose a couple questions for the CGM community. What if I tell you we can measure these profiles out to large radii into the transition between the IGM and CGM? Is that something you're interested in? Maybe with an emoji or a thumbs up. Are you interested in measuring these profiles to the percent level? Yes, okay, good. And then are you interested in then taking these measurements and subdividing them into your favorite galaxy characteristic, whether it's star-forming galaxy versus quiescent galaxy, et cetera, post-starburst, subdivision upon subdivision of galaxy? We can do that. So that's really, really neat. And something that I didn't have any slides for, but came up in actually discussions this past week with folks this actually happened on Monday, and then again when we started discussing the parametric model, is I've done some back of the envelope calculations, and it looks like if we have some tracer of the rotation of the CGM, in principle, we can stack and measure the dynamics of the CGM out to large scales. So this would again be the kinetic SZ. And so if you have some way to say this galaxy is rotating this way, we can actually, if we have enough galaxies, the signal to noise is there to actually measure the rotating CGM in the next couple of years. So that's, I think, exciting. So I just leave you with these questions and let you tell me if future SC observations will transform our understanding of the CGM. Thank you.
Yes, yes is the answer. This is a great talk. I loved today's talk. It allows me to kind of dream wildly about the future from the near term, what you were just talking about, dynamics of the CGM, all the way to 2036, which will probably turn into 2040 if we're honest. Okay. So what we're going to do now is we are going to take a short break. I know everybody probably wants one, needs to digest some of that information, look at the Slack, digest what's there, react to the questions, pose questions. We will come back in 5 minutes, so 12 after the hour. Okay, so we'll come back at 12 after the hour. I'll introduce the panel and we'll get our exciting discussion going. Thanks again to both speakers, and we'll see you in 5 minutes.